Hello viewers and welcome to a new STM32 World tutorial video. In this video we are going to talk about the ADC peripheral in STM32 microcontrollers. And if you watch this video to the end, you will be able to measure multiple values, multiple analog values with the ADC. You will be able to use DMA to let the peripheral run on its own without actually hurting the performance of the microcontroller itself, the CPU core. So please stick around, hang around to the end, and as usual, if you like this video, please do like and subscribe down below. If there's something you don't like about this video, please let me know in a comment so I can improve in the future. As usual, I have created a project called STM32 World ADC. I am going to run on my STM32 World board, which we have there, with the ST-Link device connected. You can see I still have the SD card hanging off it from my SD card video because I plan to make another video with that. I also have a display attached, and I actually have another board below, but I'll get back to that later. Today we're just going to use the board as it is and nothing else. I have created a project. I have configured, as usual, I have configured the clock configuration to run at 168 megahertz. While we're in here and showing this, please pay attention to the ADC APB1 and APB2 timer clocks, which are running at 84 megahertz and 168 megahertz respectively. I have also created the serial I/O, and I have created the LED GPIO. If we try to, in the source code, I have created the redirect, so printf will go to my UART, and down here in the loop I print a statement every second. If we try to run this, we have the output here, and you can see it is starting and it's counting, and it is showing how much loops it managed to do in that second. So about 21 million. We will see as I add features how much that slows down. That will give us a good understanding of the impact of what we are doing. So that's about it. Let's look at the ADC. Now, if we go into analog configuration up here, you can see that this device have 3 ADCs, analog to digital converters. It's got 3 of them, and each of these 3 have multiple channels, so 16 channels in that. Okay, 8 channels in ADC 3, not sure why there is a difference, and a bunch of channels in ADC 1. Now, the interesting part is we will do this video without hooking anything up. We'll just run it on the CPU core, the MCU itself, because if we look down here, it actually have 3 internal channels. They are wired up internally in the CPU, so you can measure the temperature of the CPU itself. That is not necessarily the room temperature. It will probably be quite a bit warmer. That is to be expected. We also have an internal reference. Now this STM32F405 MCU does not have an external VREF reference voltage pin. If you have more pins, the 100 pins and stuff like that, you might have an external voltage reference, but this one actually have an internal voltage reference, and we will be using that. It also have the V battery channel, but so I'm going to enable all these channels, and I plan to measure all these channels and put it into DMA. So let's look at the configuration down here after we enable this channel. We will be running the ADC in independent mode. We will run it as fast as we can. That is the prescaler divided by the clock divided by 4. We will measure 12-bit. That is the full resolution. We can turn that down if we are less interested in precision. And we will leave the rest of these values as they are. Down here you can see the ADC conversion mode. How many do we want to do? Well, we will want to do 3 because we actually have hang on. Here we can say we want to trigger this. How do we want to trigger the conversion? By default, it's a regular conversion launched by software. That means the software say, okay, go out and check. But we want to run this automatically. So let's look at the options. And an option down here is to use timer 8 trigger out event. So actually let's select that timer 8 trigger out event. Before we continue with this, let's configure that timer. So we go over to the timer and we look at timer 8. I want that timer to be clocked from here. I want that to be clocked from the internal clock. Remember before I mentioned timer 8 is actually hanging off APB2. So it will get a clock of 168 megahertz. So the first thing I want to do with this is I want to divide that by 168. And remember from earlier videos, you need to subtract 1 from that. And then let's run at 1000 minus 1. That means that this will divide it down to 1 megahertz, and this will be divided by 1000. So in other words, I get an update every 1 millisecond, 1,000 times every second. Now, when we get this trigger run out, this timer run out, what I want to do is I want to set an update event. So every second, 1,000 times every second, this one will send an update event. Now we can go back to our, actually let me, global update interrupt. Let's fire an interrupt as well. I don't think I'm going to use it, but it won't hurt. So here we will trigger this conversion of the ADC using the timer 8 trigger out event, and then we have our 3 measurements down here. If we look at the first one, that is our internal temperature sensor. You can say how long you want to sample it. The longer you sample, the more precise it will be. So let's do 144 cycles for that. Here we have our VREF, and we want to do that for 144. And down here we have our battery channel, and we want to do that for 144. So every time this is triggered by the timer in background, it will run for probably around 500. I can't do that in my head. 550 right? Cycles. So that will run by itself. I also want to enable the DMA. So the DMA, I want to say ADC1 DMA. There, I want to run a circular buffer. That means the buffer will be divided into 2, and each buffer will be handled by itself. And then I want to go over to the interrupt settings, and you will see the DMA interrupt is always enabled. So in other words, now the ADC is configured the way we want it. We have configured the DMA interrupt and the DMA, and we have configured the ADC to be triggered by the trigger out event from our timer 8, which we have also configured. So let's generate the code. There we go. And as usual, I do not like the tabs, so let me format that. Let's try to build it and just make sure that it is still building. And it is indeed. So let's start filling in the ADC code in this. First, let's do some defines that actually we can reuse in the code later. So private defines up here. I have defined an ADC resolution. I actually don't think I use that, but that is 2 and 12, so 4096. I want the buffer size to include 10 DMA samples, so it will be called about 100 times every second, right? Because it will take, and the DMA buffer size, I want that to be 3 DNA samples, so 30 values in this, because we have 3 channels we are going to use. So let's go down under our private variables down here and let's define the DMA buffer. Now, private variables, let's also define actually I want duck. I want the final variables to be here, so we will end up with an analog VDDA, analog voltage, and an analog temperature, and an analog VREF. That is the values that we are going to end up with after this. I also created a callback counter just to see if things are actually working. So next up, I want to create those DMA callbacks, and they will be down here in the code 0 seconds. After our print redirect, we can do these. So when the buffer is half used, this will be called, and it will call a process buffer function with the part of the buffer. So when it is half finished, conf half callback, it will start in the beginning of the buffer because it will now be dealing with the second half of the buffer. When it's completely converted, it will start with the middle of the buffer and then work toward the end of the buffer. So it is quite simple. So let's create this one as well, and all I want to do right now is I want to increase my callback so I can keep track of whether these are actually being called, executed when we start this. Now let's go down and start all this up. First of all, we have to fire up our, after we start, we can fire up the timer in interrupt mode. Timer has already been configured, so it will just fire up, start interrupting, which is fine. Then we can start our DMA, our ADC in DMA mode. I have that there. So I basically start the DMA, and it is ADC1. I will pass it a pointer to the DMA buffer. This one expect a 32-bit pointer. I don't know why, because they're not using 32-bit. Oh, by the way, let me show you that. If we go into the ADC DMA, you will see that it is using half words. So basically 16-bit values. That was why I didn't explain that at the time. Up here, the DMA buffer, it is a 16-bit values because the resolution is only 12-bit, so it would be silly to use 32-bit for that. So I pass it a pointer to that DMA buffer, and I pass it double the DMA buffer size. This was how we defined it up here. It is defined 2 times the DMA buffer size, and the DMA buffer size is 30, so it'll be 60 values in order to make the 3 measurements 10 times. Right? We had 10 samples in the so that is about all zeros. So Let me make one other change right away, since I think we have the values now. Let me change this print statement down here to print the values that we're actually looking at. So I'm going to print out the tick. As before, I'm going to print out the loop, but I'm also going to print out the callback. So how many times have the callback up here actually been called? I'm going to print out the VDDA as an analog value, floating point, double. I'm going to print out the vref, and I'm going to print out the temperature, and that is it. So let's try to run this, see if that works. It compiled here. So there you go, and you can see the callback is actually being called 2 times every second. That is actually lower than I expected. So the timer must be the timer. How did I configure? If we set that to 100 minus 1. I was expecting roughly 100. So it builds. Let's try to run it. Still only running 2. What happened there? This is update event. Why didn't this make any change at all? Did it generate the code? This built. I'll worry about that a little later. Let's callback. So the callback is called, well, as long as it's called more than once, it should be okay for us to calculate. We still get the values. So let's start looking at the actual process buffer up here and see what we have to do to make that work. First of all, I want to create, I don't want to use the individual values. So what I'm going to do up here is I'm going to do a temperature sum, a vref sum, and a vbat sum. I'm also going to toggle the lat. Let's not do that right now because it will be way too slow. I'm going to go through these DMA samples. I'm just going to add, and then I'm going to divide by the number of DNA samples. That should give us the actual values, an average of these values that is measuring. It can fluctuate a little bit. Finally, I'm going to do the calculation, and let me start by copying what I created before. Now, internally, if we're looking at the MCU, right here, you will see that there is a V battery pin there. There's a VDD, VSS. Here we have an analog input. Now, on my board, this is just simply hooked up to the normal supply voltage, so that can sort of fluctuate a little bit. And it is actually possible to calculate the value of that VDDA based on the internal reference. So if we look at this, we can see our VDDA is actually, we are using some calibration value here. And this is actually the interesting part. So if we look at this one and open the declaration, you can see that in the header files, there is a calibration. It's calibrated to 3.3 volt, 3300 millivolt, and in an address in the ROM, there is an internal reference value calibrated at 30 degrees. So it is actually each individual STM32 have a calibration value built into it. It also have calibration for the temperature sensor. It's got two set points. It's got at 30 degrees and at 110 degrees. And what you do is you assume that the ADC is linear. So with those two values, you can do a straight line between those two, and then you can calibrate your temperature measurement based on these values. Bear in mind that this one, and this one are values. This one, the ones that are called ADDR, are actually addresses. It's a pointer to a 16-bit value, so we need to dereference that if we're using it. So if we look over here, it is my VREF 3300. I divide by 2, so it's 3.3 because I'm making it a floating point. And then I take whatever value is at calibration address and I divide that by my average VREF. That gives me the VDDA actually. What is the analog voltage? I can also calculate the exact value of that VREF. What is my internal reference running at? If we go, where are we there? Sorry. If we go into the official documentation of the STM32F405 datasheet, we have it here. Let's look at that and see how is that actually defined. Oh, I'm getting it. I don't know why STM's website is a bit slow at the moment. Here we go, we got it. So if we search for so irritating. If we search in the datasheet for vref int, there, we'll see that our internal reference voltage is between 1.18 volt and 1.24 volt, and typically 1.21 volt. So we expect a value about 1.21 for the vref, which is basically the VDDA divided by the resolution multiplied by the actual vref we got up here. The temperature can also be calibrated. I'm basically doing a linear approximation of this, assuming it's linear, and I'm using the calibration values to calculate it. So that is all I'm doing. And let's try to build this. Does it build? Nope. It doesn't have these three. I forgot to define those, I think. Let's do them. Do I need them? Oh, we can do them globally. I didn't really. Oh, we can just define them up here. We're using the same 16-bit values for the average as we have. There's no point in going bigger than that. Let's try to build it. Let's try to run it. So there we go. Our VDDA is 3.28 volt, and I don't want to hook up a multimeter right now, but believe you me, it is about slightly less than 3.3 volt. My internal reference is calculated at 1.2 measured and calibrated, and my temperature is internal temperature is about 40 degrees. I have mentioned in earlier video I am in the tropics and it's probably 36 degrees or so in my office, so a couple of degrees higher than that is to be expected as the internal temperature of this. Let me sort out why it doesn't update as much as I expected. So we get 2 callbacks. Wait. There's something seriously weird here. Does it change? It never changes. Okay, that is a problem, because this one should just be counting up. So CB, let me look at the my CB is there. I update it down there. Let me make one change I don't think I did earlier. This is, I don't really want the global interrupt. Maybe that messes up break interrupt. So let's look at the timer configuration. 168. I actually want that one to be 1000. I think that's correct. Repetition auto reload shouldn't be necessary with this, but we can try to enable that. I don't think that makes any change. And this is running off the internal clock, and it sends an update event, and it is timer 8. And if we look at the ADC, this one is triggered by the generate code. Let's try to fire that up. Okay, I'm going to pause this video a second while I figure out what happened here. This is not behaving the way I expected. Okay, I am back and I figured it out. If we go into the STM32 CubeMX, I overlooked a setting down here. This DMA continuous request was set to disabled if we have to enable that. And that means that meant that it would only after I started it, there, it would only do it once. But when I set it to continuous request, it will keep waiting for the trigger out event, and then it will run. And again, I set the timer value over here. I set that back to 1000, so it sent me a interrupt every millisecond. It will do a timer in its timer update event, and if I go into the code just to make sure that we get what we expect, it's always good to have an idea of what to expect. We have 10 samples, so we would expect, if I get an update event every millisecond, and I have to measure 3 values, but every 100 milliseconds, and I have 10 sample values of that, I would expect the callback to be called 100 times every second. So let's try to build this, and let's try to run it. There. And there you go. Now the callback is being called every 100 milliseconds, and you will see these values, they didn't move before at all, but now they are changing slightly. I hear you say that value is a bit high. I do have some cooling spray on hand, so let me try to chill the processor. I do that. Well, actually, let's put that on video. So where is my device? Here. So I have some cooling spray and I'm going to chill the CPU quite a lot. And let's see what happens if we go back here. And you can see it went down to 20, what was the lowest? 25 degrees. And now it starts working up again. I said cooling spray. It's actually not a cooling spray. It's contact cleaner, but it gets cold. So it will have the same effect. So that is about all she wrote. As you can see, it is very, very simple to use. In an earlier video, I showed how to use the digital to analog, the DAC, also using DMA and even using it with the FreeRTOS one channel normally, and I did a dual channel one in FreeRTOS where I triggered the different tasks with a semaphore, or was it a queue message? I don't remember straight off the top of my head. In this case, we're not using FreeRTOS, but we are measuring 3 different values every time. And an interesting thing is, if we look down here, remember we started up, it doesn't affect the MCU performance at all, because all this is running in background. All it's doing in this is this little average thing up here, which doesn't take that many cycles. There's some floating point as well that takes more cycles, but it is still, it's a fairly lean computation, and the MCU have plenty of time to do other stuff while this is literally just running in the background. Now, every time you use DMA, I think what confuses many users is, if we go into the ADC again, DMA settings, the circular mode. And I want to spend a few minutes explaining that in more detail. So basically what we have is, we have a buffer here, but we make that buffer double the size we needed. You see, the DMA buffer size is 3 for 3 values of the DNA samples, right? So 30 byte or 30 samples will be used for that, but we use a double of that because we use double of that size because we need 2 halves of this. And then what happens internally is that we get 2 interrupts. We get one when the, actually let me move this, it's more logical because the half one comes first. Doesn't matter, but so first it will start from the beginning of the buffer. It will go to when it reaches the half point. Then it will start to write the second half of the buffer, and that means we can process the first half. It will not be touched. So we start the address of the first element in the buffer. That is what we're processing. When it's done, that means you reach the end. It will start all over again because the buffer is circular and we cannot touch the first half of the buffer, but we can start using the values in the second half of the buffer. So it is 2 halves of this buffer when it's running in circular mode. And that means we never ever risk that the values that we are calculating is being overridden by the DMA. We're not in control of that. So it is very important to make that understanding. And the trick here is just that this one, the callback, must complete before the next one happens. If the next one happens before this one is complete, then we will have trouble. But as long as you can make sure that this one is completed much faster than this one, then it will work. And that is about it. It is exactly the same we did the other way with the DAC. The only difference was it went the other way. This one is going from the peripheral to memory. The other one went from memory to the peripheral. But in this case, we just simply get the data into the memory in this circular buffer, and the DMA peripheral will take care of the pointers and fire those interrupts that is configured over here, right? We will get those DMA streams global interrupt whenever it is time to handle the other part of the buffer. So it is actually surprisingly simple to use DMA for these things, and as you can see, it takes almost no CPU cycles to do this. So we got plenty of CPU left to do other things while this one is cycling off. We also got values pretty much around where we expected. I think this one looks a little bit high. It is possible that my calibration is not correct. If any of you spots a mistake here, please do let me know. I actually tried this on a black pill board, and on my black pill board I got around 30 degrees, 32, 33, 10 degrees lower than this. I am not sure if it is because the STM32 F405, I'm running it quite a lot quicker than the black pill board is running, so I don't know if it's that, if it just gets more hot than the F411 that I have on my black pill board. But that's it. As I mentioned in the beginning, please do like, if you're still here, please do like and subscribe, and let me know if there's anything you think I could improve in this video. And as usual, the source code of this is in the STM32 World STM32 Fun repository on GitHub. There's links in the channel somewhere. You can find it. So that is about it. Have a wonderful rest of the day.